We now consider the number of significant partial waves in a scattering problem. For small energies, the shifts delta L will be appreciable only for small values of L. As the energy becomes larger, more and more partial waves become important. This can be understood by means of classical arguments or quantum arguments. In the classical argument, we consider the following situation. Suppose we have a scatterer at the point O, and an incoming particle is coming along this line and getting scattered into this direction, given by this dotted line with these arrows. Now let Q be the point of smallest distance from the scattering center, and the distance of that point from the scattering center is called the impact parameter, and the trajectory at the impact parameter will be normal to the line from the scattering center to that point Q. And therefore, the angular momentum of the particle at that particular point can be given as its momentum at that point P times the perpendicular distance, which is B. So that is equal to the angular momentum. Now for a particle that is coming with an energy E, we can define K is equal to square root of 2me by h bar square, or we may write P as h bar K, and then this equation becomes h bar K times B is equal to L. Now the quantum mechanical values of L square is given by L into L plus 1 times h bar square, and for large values of L this may be approximated as L square times h bar square, and therefore L may be approximated as L times h bar. So L, which is equal to approximated as L times h bar for large values of angular momentum quantum number L, can be written as so this is equal to h bar K times B. Now cancelling out the h bar terms, we get L is approximately K times B. Now assume that the potential has a significant influence only in a region of distance r0 from the center, the scattering center O. So the region that is enclosed by the sphere of radius r0 about O. So only particles that come within this region at distances less than r0 get affected by the scattering potential. So they are the only partial waves, or they are the only particles that get affected significantly by the scattering center, and therefore in computing the scattering cross section we may include only those particles. So this implies that the impact parameter of such particles should be less than r0. Otherwise, they will fall outside the sphere of influence of the scatterer and therefore will not be affected significantly. So B should be less than r0, or in other words, K times B should be less than K times r0. But K times B is approximately L. Or in other words, the angular momentum quantum number of this incoming particle should be less than equal to KR0, so that it will be affected significantly by the scattering center. and therefore we only need to consider partial waves with L values that are less than or equal to k times R0. Now we can arrive at the same result using quantum mechanical arguments as well. So we see that the amplitude of the Lth partial wave is proportional to JLKR, which is the spherical Bessel function of order L. Now for L is equal to 0, J0 has a maximum at R is equal to 0, and for all values of L greater than 0, JLKR will be small as for small values of R, and it increases and reaches a maximum, and that maximum is approximately at KR is equal to L, approximately KR is equal to L, and then it decreases and it falls off rapidly as R becomes very large. So the maximum of JLKR is approximately at KR is equal to L, or R is approximately equal to L by K. Now this partial wave is affected significantly by the scattering potential only if the scattering potential is significant at points where JLKR is significant, and JLKR is maximum approximately at R is equal to L by K, and therefore only if the partial wave's maximum, that is L by K, is less than the range of the potential, which we call as R0, is the partial wave affected significantly by this potential. Otherwise, the maximum of the partial wave will fall outside the range of the potential, and on either side of the maximum, the Lth partial wave has amplitude that is very small, and therefore a partial wave, in order to be affected appreciably by the scattering potential VR, should have a maximum at point which is less than the range of the potential. So L by K should be less than R0. Otherwise, L should be less than K R0. And this is exactly the same result that we obtained with the classical arguments. Now we consider what is called a Ramsauer-Townsend effect. If the bombarding energy is small, that means the wave vector k is very small, and therefore k times R0 is also very small. And therefore, for L greater than 0, k R0, so L, that is for L greater than 0, L will be greater than KR0 as well, because KR0 is extremely small, and L can take values 0, 1, 2, 3, etc. And therefore, if L is not 0, that is, it is greater than 0, it can be 1, 2, 3, etc. And therefore, it should be greater than KR0. So for extremely small values of K, that means for small values of energy, the only important partial wave is the one with L is equal to 0. Only for L is equal to 0 is L less than KR0. So for such scattering, only the S wave scattering is important. It's only the S wave that gets affected significantly by the scattering potential. So the total scattering cross section will be approximately equal to the contribution due to the S wave contribution, and which is given by 4 pi by k square times sine square delta 0. Now, if delta 0 is equal to pi, then the scattering cross section sigma will be 0. And Ramsauer and Townsend observed extremely small cross-section for electrons of rare gas atoms at bombarding energies as small as 0.7 electron volts. And this is the Ramsauer-Townsend effect.